We've alluded to the idea now for several topics that we might be able to take the derivative of the derivative, which we would call a second derivative. And in fact, as we start doing that, we just refer to them as higher order derivatives, third derivatives, fourth derivatives, and so on and so on. So the first thing we want to do before we start getting into some of that process is let's talk about what the notation is going to look like. So let's consider the following function. And I'm going to let kind of bookend this with notation. I'm going to say y equals 4x cubed minus 3x squared plus 7x minus 5. So this is how it would look in terms of y. That's a y equals a function of x. I'm also going to go ahead just kind of over here and say, let's use the f of x. Let's use function notation. And so as I differentiate, I'm going to let the notations kind of work on the outside. And I've given us a nice easy polynomial where I think we can already see what the derivative is going to look like, and then it's a pretty easy derivative to take of the derivative. So let's do the first one. Dy dx, that's how we express the rate of change of y with respect to x. And we already know how to do this. This is going to be 12x squared minus 6x plus 7. And for our function notation, that's going to equal f prime of x. So you can see here I've got both notations going. Here's dy over dx, here's f prime of x, and the middle part is the part I kind of expect you to be able to follow pretty easily at this point. So the question in front of us now is, how do we notate this idea of a second derivative? And the notation looks a little bit different for both. This would be Leibniz notation. This would be Newton's kind of function notation here. Let's start off with the Leibniz notation here. We're going to apply what's going to look like an exponent of 2. And it's going to look like d squared y over dx squared. That's the notation for second derivative. And it's very important that you express these 2's in the right place. This literally reads, as the second derivative of y with respect to x squared. And you can kind of see that notation. It's the second derivative of y with respect to x squared. We have taken the derivative again. Now then, it is going to be just as simple as, what's the derivative of this function? Well, that's 24x minus 6. Now then, over here for the function notation, we just add an additional prime. So f double prime of x would equal 24x minus 6. I can take a third derivative. I can say that the third derivative of y with respect to x cubed is equal to, in this case, 24. And I can say the third derivative like so. Now then, we can keep doing that here with the Leibniz notation. Obviously, over here with the function notation, you know, theoretically, we were taking the 10th derivative of something. You wouldn't want to put 3 tick marks. So first of all, the rate of change of 24 is 0. We are now taking the derivative of a constant. So we would express that as the fourth derivative of y with respect to x to the fourth. Now then, after 3, it's pretty common practice. And in fact, some textbooks and some places will do it starting at 3. But if there's more than a couple of derivatives here with the function notation, it gets expressed like so. Rather than just putting that many tallies or that many prime tick marks, you just kind of notate it. It almost looks like an exponent, but you'll see it in parentheses. So either way, this represents the fourth derivative of y with respect to x to the fourth. This would be the fourth derivative of f of x. And you can see the process was pretty easy. This was actually the part that I kind of would expect anybody to look at and know how to do. It's the notation that was really the focus of this particular video. So the process of taking higher order derivatives is you just kind of keep repeating our process. There's not anything necessarily new. There's no new rules that are going to come out of this. It's just taking the derivative of the derivative, however many times you need to do to find the derivative that you're looking for.